Hello, I am Prayash Pavan Sarvavara and I'm here with a basic presentation on the topic of waveguides. Firstly, let us go to content of today's presentation. Firstly, we'll be going over basic introductions of to waveguides, then its features and different type of waveguides like rectangular, circular, different advantages, disadvantages, application, and finally conclusion of the entire presentation. Firstly, let us go to introduction to waveguides. At frequencies higher than 3 GHz, the transmission of electromagnetic waves along the transmission line and cables become very difficult. This is mostly due to the loss that occurs in both solid electric dielectric needed to support the conductor in the conductors themselves. Metallic tubes can also be used to transmit electromagnetic waves at above frequencies. Now, what is the definition of waveguide? Hollow metallic tube of uniform cross-section for transmitting electromagnetic wave by successive reflection from inner wall of the tube is called waveguides. As you can see here, the direction of wave propagation and what are the waveguides. Then, some basic features of waveguide. Waveguide may be used to carry high energy between pieces of equipment or over longer distances to carry transmitter power to antenna or microwave signal from an antenna to a receiver. Waveguides are made from copper aluminum. These metals are extruded into long rectangular or circular pipes. An electromagnetic wave to be carried by waveguide is injected into one end of the waveguide. The electric and magnetic field associated with the signal bounce off the inside wall back and forth as it progresses around the waveguide. EM wave field configuration within the waveguide. In order to determine the EM wave field configuration within the waveguide, Maxwell equations should be solved subject to appropriate boundary condition at the wall of the waveguide. Such solution give rise to a number of configuration. Each configuration is known as a mode. These for the following are the different modes possible in a waveguide system. And in component of electric and magnetic field intensity in a waveguide, as you can see from the diagram here, the possible types of mode: transverse electromagnetic wave. Here, both the electric and magnetic field component, both electric and magnetic field component are zero. Transverse electric field wave. Here, only the electric field is purely transverse direction propagation, and the magnetic field is not purely transverse. I Ez equal to 0 and Hz not equal to 0. Transverse magnetic wave TM. Not only magnetic field is transverse to direction of propagation, and electric field is not purely transverse. Ez not equal to 0 and Hz equal to 0. Hybrid wave. Here neither electric nor magnetic field are purely transverse to direction of propagation. I Ez not equal to 0 and Hz not equal to 0. And again, as you can see here, for TE mode and TM mode, electric field and magnetic field direction, etc. And also when we have the wave propagation direction compared to it. Now, rectangular waveguide. Any shape of cross-section of wavelength can support electromagnetic wave, in which rectangular and circular wavelengths become more common. A waveguide having rectangular cross-section is known as rectangular waveguide. Dimension of waveguide, which determines the operating frequency range. The size of the waveguide determines its operating frequency range. The frequency of operation is determined by the dimension A. The dimension is usually made equal to one half the wavelength at the lowest frequency of operation. This frequency is known as cutoff frequency. At cutoff frequency and below, the waveguide will not transmit energy. At frequencies above the cutoff frequency, the waveguide will propagate energy. The wave path in a waveguide at various frequencies. As you can see here, A for of A at high frequency, at medium frequency, at low frequency, and at cutoff frequency. Wave propagation. When a probe launches energy into the waveguide, the electromagnetic field bounces off the side of the wall of the waveguide as shown in the diagram above. The angles of incidence and reflectance depends upon the operating frequency. At high frequencies, the angles are large and therefore the path between the opposite paths is relatively long as shown in the figure. At lower frequencies, the angle decreases and the path between the sides becomes shorter. When the operating frequency reaches the cutoff frequency, the wavelength simply bounces back and forth between the both side walls of the waveguide, and no Just no forward motion occurs. At cutoff frequency and below, no energy will propagate. Cutoff frequency. The exact size of the wavelength is selected based on the desired operating frequency. The size of the wavelength is chosen so that the rectangular width is greater than one half the wavelength, but less than the one wavelength at operating frequency. This gives a cutoff frequency that is below operating frequency, thereby ensuring the signal will propagate down the line. Representation of modes. General symbol for representation will be TEMN or TMEMN, where the subscript M represents the number of half-wave variations of the electric field along the dimension of the waveguide. The second subscript N denotes the number of half-wave variations of the electric field in a narrow dimension of the wave. TE1,0 node has the longest operating wavelength and is the design as the dormant mode, and it is the mode for the lowest frequency that can be propagated in a waveguide. Now, expression for cutoff of wavelength. The standard expression for a waveguide, the cutoff is given by the following equation as shown here, where A and B are measured in centimeter. Circular waveguide, a hollow metallic tube of circular wave section transmitted by a successive reflection from the inner wall tube is known as circular waveguide. Circular waveguide has many special applications in microwave technology. It has advantages of great power handling capacity, lower attenuation for a given cutoff line. However, the disadvantage is somewhat greater size and weight. The polarization of the transmitted wave can be altered due to minor irregularities of the wall surface of the circular guide, whereas the rectangular waveguide, the polarization is fixed. Advantages. Waveguides have several advantages over two-wire and coaxial transmission line. Skin effect tend to increase the effective resistance of the conductor. Although energy transfer in the coaxial cable is caused by electromagnetic field motion and the magnitude of field is limited by size of the current carrying area of inner conductor. The small size of center conductor is even further reduced by skin effect, and energy transmission by coaxial cable become less than the waveguides. Disadvantages. The physical size is the primarily the low frequency limitation of waveguides. The width of the waveguide must be approximately half a wavelength at frequency of the wavelength to be transported. The waveguides are difficult to install because of their rigid hollow pipe shape, and special coupling at the joints are required to ensure proper operation. Costs are more and decreases the practicality of waveguide system at any other than microwave frequencies. Application of circular waveguides. Rotating joints in the radar is to connect the horn antenna feeding a parabolic reflection, which must rotate for the tracking. The TE01 mode is suitable for long-distance waveguide transmission above 10 GHz. Short and medium-distance broadband connection could replace shared coaxial microwave links. To reduce attenuation loss can operate above other frequencies. Now, finally, for conclusion, the electromagnetic waves can be guided along a desired route not only by transmission line but also by hollow pipes, dielectric coated surface, or dielectric rods. The typical of all these hollow waveguide that they cannot support TEM wave types but also support TE and TM wave types. They cannot transmit energy below a lower frequency known as cutoff frequency. Waves of frequencies above the cutoff frequency propagate without attenuation due to loss of mean material. Then wave frequencies lower than the cutoff frequency known as evanescent nodes are exponentially integrated, do not propagate at all. Among hollow metallic waveguides, the most important are those of rectangular cross section. There are infinite number of both the EM and MM node that can propagate among such wavelengths. So finally, this was it for the waveguide. I hope you had a good time listening to the explanation.